Hi, this is Roger from Kanka Labs, and today we'll talk a little bit about transformers, or better, some properties of transformers. Well, transformers are notorious about, even if you buy them from quality companies, that you don't always get all the data you need for calculating their properties or selecting them for your purpose. So we'll delve a little bit into the very simple math of transformer properties. We'll not deal with them in detail, but we only will need Ohm's law and Ohm's law of power to get unknown properties of a transformer. Well, we'll take as an example this little beast here. You already can read probably in high definition some of the properties, but we'll leave that out for a moment. And first of all, let's sum up which properties are important for designing your circuit or for selecting a proper transformer. So let's start with some of the basic properties. We of course have the power P of the transformer, which is the maximum power it can transmit without doing any damage. Then we have the rated voltage. Pardon me if I use the letter U here for voltage, but that's the convention in Germany. So we have the rated voltage U. Then we have the rated current I. And we have the open circuit voltage, because you might know that if you put no load to a transformer, then the open circuit voltage can be much higher than under load the rated voltage. So we call that the voltage OC, UOC. And then we still have the internal resistance R. And why is that? Well, you can look at, if we only take one side of a transformer, of course we have the inductance here, but in series with the inductance is the internal resistance R. Usually that is the copper resistance, but there are also other effects influencing the internal resistance, which not only have to do with the copper resistance. So we'll see in a minute by comparing the measured internal resistance compared to the copper resistance, that really is a difference. And then you sometimes want to know, well, which maximum load resistor can I put here on the output terminals of a transformer for not to get over the maximum power. Now let's start with the first three ones, and usually you only need 2 of the 6 values here to calculate all the others. And the most common situation is that your transformer only gives you 2 of the 3 values: power, rated voltage, and rated current. Now that's quite easy if we know from the definition of power that power is simply voltage times current. That if we know the rated voltage and the rated current, then we can immediately calculate the rated power, that is the total power your transformer can output on the secondary side. I'll use the index R here for the rated values. So that is quite simple, and by simply playing around with the formula, if you want to know the maximum rated current and you have given the power and the voltage, that is a simple P divided by the rated voltage, and last is if you have the rated voltage. If you want to know the rated voltage, then it's simply P divided, the power divided by the rated current. So that was the easy part. If you have two of these values and want to know the third one, these are the easy formulas simply from the definition of power, that power is voltage, rated voltage times rated current. And from that definition, we also can easily calculate what is the maximum load resistor we can put here on the secondary. So here would be placed our load resistor, and the load resistor must be, for not consuming more power than the maximum rated power, it must be greater either than P, the power divided by the squared rated voltage, or if you want to calculate it with the rated voltage instead of the rated current, then the load resistor must be greater than the rated voltage squared divided by the power. And so that was also quite easy. So now you know what is the maximum load resistor. If you have an ohmic load, if you have complex loads, that's a whole different story. But for ohmic loads like light bulbs or resistor, heaters, etc., that is simply the maximum load resistor for not just going over your maximum power rating. So now we have the formulas for the dependency of power, rated voltage, rated current, and the maximum load resistor. What is quite often missing in the data sheets of transformers is the open circuit voltage and the internal resistance, and we now take a closer look at them, and there'll be at least one surprise for one of you, that it's not as easy as it looks at the first moment, especially when it comes to the internal resistance. So, to investigate a little bit further the internal resistance, we just measure this little transformer here, which has one primary and two secondary windings. We just measure one of the secondary windings with our LCR meter, and what's not interesting for us, I can only measure here at 100 Hertz as the lowest frequency. 50 Hertz would of course be better. So what's not so interesting here is the series inductance of the secondary winding, but what is more interesting is the equivalent series resistance, that is in our case 24.5 ohms. So let's write this up. 24.5 ohms. And you might think, well, this must be the DC resistance. Well, no, it's not, because it takes always a little bit longer for the LCR meter to measure the DC resistance, and it displays as 13.6 ohms. So we have two different values. The copper resistance is 13.6 ohms, while the series resistance, so our DC, is 13.6 ohms, but the ESR, or the series resistance, at 100 Hertz, we should add this, is higher. It's 24.5 ohm. So now what's the right value to calculate, and how does this influence our still missing open circuit voltage, and well, what can we do with it, two values? So we still don't know now what is the right value to choose for doing further calculations, and to simplify things a little bit, or to make them a bit clearer, let's take a different view at the secondary side of a transformer. Now, of course, we know a transformer, first of all, is a voltage source. Of course, an AC voltage source. And this voltage source has, as a voltage, the open circuit voltage. But we know there is in series the internal resistance. We still are not sure, is it the ESR, this equivalent series resistance we measured, or is it only the DC resistance? And then on the output we have our load resistor. So here are the two terminals of the winding, a voltage source in series with a resistor, and on the output we have a load, and the upper side of course is then connected here that way. So if we put no load on our secondary winding, then of course we can measure the open circuit voltage also here, because then we have no voltage on the resistor, because there is nothing flowing through it, or except for the nanoamps or microamps through your multimeter. But anyway, without a load, and that's why it's called open circuit, we can measure the open circuit voltage simply here at the output terminals of our secondary winding. And of course, then if we put a load on the output terminals, then here we get a voltage divider, and now we would measure the voltage under load. And if our load is the maximum allowed resistance or the maximum allowed load, then the voltage here at the terminals will drop to the rated voltage. Aha, well, now we have something that we can do some calculation with, because depending on which value we are searching, we again either measure, we have from these three values, at least two are given or can be measured. So either we have the rated voltage and we can measure the, for example, the open circuit voltage, then we can calculate the internal resistance, or the other way around. So two of the values again are sufficient to calculate the third one. So think for it for a moment. We only need two of the values to calculate the third one. So, and by a lucky chance, for this transformer, the open circuit is given in the data sheet. We could also, of course, connect it here to mains voltage and measure the open circuit voltage. But now we can do some math and compare what we get for the internal resistance. And the formula or the equation is quite simple. The internal resistance equals the open circuit voltage minus the rated voltage divided by the rated current. And for this transformers we have the values at hand. So in our case the open circuit voltage is 30 volts, the rated voltage is 24 volts, and the rated current is 0.2 amps, and we even don't need a calculator. We can do the math in our head. 6 volts divided by 0.2 gives us 15 ohms. Excuse me, it's better to have a calculator. 30 ohms. So for this transformer, where we already measured the DC resistance and the equivalent series resistance, we get 30 ohms, which is quite near to 24.5 ohms. So you should not be trapped to use the measured DC resistance for further calculations. You should use the either measured with an LCR meter or calculated by these three either given or measured values: the open circuit voltage, the rated voltage, and the rated current, and that gives you the series resistance, or at least you're quite near to it. So let's remember this quite important fact. When you are dealing with the internal resistance of a transformer, you should not use the measured DC resistance, which you measure with your multimeter, but either you measure it with your ESR meter, if you have one at hand, and ideally at 50 Hertz in Europe or 60 Hertz at other regions. And no matter how you call it, series resistance or equivalent series resistance, and if you cannot measure it with an LCR meter, then you can only calculate it in a simple way. You just measure or take from the data sheet the open circuit voltage minus the rated voltage divided by the rated current, and then you get your internal resistance. So that is quite an important result. Do not use the DC resistance. The DC resistance becomes important when you want to calculate the short circuit current, but you should never short circuit your transformer because it will overheat. For the under normal conditions, the internal resistance should be either measured with an LCR meter or calculated by either given or measured values like here. And then we only have one final value, because you usually don't get the open circuit voltage, so we can play around with this formula. And if we on the other side have measured the internal resistance with an LCR meter, we can also calculate the open circuit voltage. And that is simply the series resistance or internal resistance, or ESR, times the rated voltage times the rated current plus the rated voltage. And so these are our two final equations or formulas concerning the math that you, in 99% of all cases when it comes to dimensioning a circuit or selecting a transformer, are absolutely sufficient to do, well, all the calculations or to get all the unknown values. So let's remember, here we had from power, voltage and rated current, we had the three formulas where when we only have two of the three values, how we can calculate the third one. Here we have the formulas to get the maximum ohmic load resistance for not going over the maximum power. And here we have the final two formulas to calculate the series resistance or to calculate the open circuit voltage, depending on if you have an LCR meter present or do at least one or two of the measured values. For example, here you would have to measure the open circuit voltage. So that was it for a short introduction about the engineering math that you need when using power transformers. Thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.